My name is Karol Myszkowski, and I am going to present our work on the effect of geometry and illumination on appearance perception of different material categories. Before I move to our project presentation, I would like to say a few words about Professor Cooney, who was my mentor in my academic career. First time I met Professor Cooney in 1996. I was working at the time at a software company in Tokyo developing global illumination software. And the owner of the company introduced me to Professor Cooney and arranged a meeting at his laboratory at Tokyo University. Professor Cooney was very generous in terms of his time, showing us abundance of projects, and toward the ends, he handed us a pile of the Visual Computer journal issues. I don't need to say this probably, but you will know that I read all articles there because there were such times that we were hungry for knowledge in computer graphics. I came back to Professor Cooney laboratory a number of times, mostly seeking for the support in terms of literature, and he was always welcoming me there. In 1993, Professor Cooney founded Aizu University, and I joined his computer science and engineering laboratory that was headed by Professor Cooney as well, as an associate professor. This was my first serious academic appointment in a truly solid academic environment. Professor Cooney invited many talented mathematicians and other computer graphics researchers, which created a very stimulating environment for research. I understood there the great role of solid foundations of mathematics in Pursue's research agenda in computer graphics. I also helped Professor Cooney to run the Visual Computer journal. I was an editorial assistant there, which gave me plenty of opportunities to meet Professor Cooney again personally. We assigned reviewers to papers, and Professor Cooney made decision on acceptance, revision, rejection of papers. And I essentially could see from close distance what is important and what criteria are important in the view of reviewers, but also in the view of Professor Cooney, who was editor-in-chief. So that was a great school for me, how to write scholarly, mature journal papers. So Professor Cooney at a certain point moved from Aizu University to Hosei University, and that was also time for me to move back to Europe. I should say that Professor Cooney changed dramatically my professional life. It's not clear whether I would be a scientist at all. I was more inclined working with industry. But essentially this opportunity to work with Professor Cooney completely changed my mind, and I stay in academia up to date. Now I would like to move a little bit with discussion of our project. Many applications involve realistic rendering, and material perception is not a trivial problem. Let me show you a couple of examples. For the same BRDF and illumination but different geometry, gloss may appear quite different. The object on the right seems to be much glossier. Similarly, for the same BRDF and geometry but different illumination, object on the right looks much glossier as well. Clearly, the material appearance under different lighting setups and geometry is a difficult problem that has been investigated in the past, but in very limited setups, limited just to considering geometry or lighting for a relatively small number of rendered images. Our approach is in the sense holistic. We collect the largest to date data set with subjective ratings of material appearance. We perform in-depth analysis on the collected data and we train a neural network that predicts material appearance for images. We demonstrate also potential of such predictor in several interesting applications. We considered measured BRDFs coming from 3 well-known data sets, which we additionally enhanced through editing using an approach presented at SIGGRAPH by Sun et al. In 2018. In total, this way, we have 520 measured materials. For illumination, we use 9 real-world environment maps that feature either smooth lighting, like in cloudy sky, or strong directional lights, like the sun, of extremely high contrast. We use also 9 different geometries that are typically used in applications dealing with tuning material reflectance properties. So in total, we generated over 40,000 distinct images, taking into account all those BRDFs, geometries, and environment maps that I just discussed. In our choice of attributes to be rated in subjective experiment, we relied on literature. We followed Toscani, who found that the main perceptual dimensions of reflectance are glossiness, lightness, and metallicness. Since we are interested in perceived gloss, we followed work of Hunter, Pelashini, and Wills, and we consider distinctness of image, which essentially measures sharpness of reflected pattern, and contrast gloss that measure contrast between highlight and surround area. We consider also anisotropy. We ran large-scale Amazon mechanical Turk experiments when the subject rate all those attributes that I just mentioned using 7-point Likert scale. Over 3,000 participants took part in our experiment. We collected over 200,000 valid responses, and we are sure that at least 5 responses we have for each image. In data analysis that I'm going to present right now, we focus on 8 material categories: wood, leather, fabric, paper, natural materials, plastic, ceramic, metals. Other materials are dropped for now, but they will be later used for training our predictor. For data analysis, we use cumulative link mix model that is tailored to handle ordered nature of Likert items and avoids treating these variables as quantitative. For post hoc analysis, we use estimated marginal means with Bonferroni correction for multiple comparisons, and the outcome of this analysis is shown in the upper row. In the lower row, we show Spearman correlations data for different material categories. What is remarkable here is that for those categories like woods, leather, fabric, paper, and natural, gloss attributes are of course of low strength, and only weak correlation between such attributes is shown. In this work, therefore, we focus on other categories like plastic, ceramic, and metal, which show high attribute strengths and also strong correlations between them. To analyze complex interactions between geometry, illumination, and material category, we further limit our discussion just to 4 geometries like strongly tessellated dragon, smooth blob, and ghost that contains both smooth and high frequency parts. And just 4 illuminations where A is smooth, low frequency illumination, and I features strong, high contrast light source. And 4 material categories that shows strongest variations between gloss attributes. The outcome of interaction analysis on the subset discussed on the previous slide is shown on the right. So one horizontal axis shows different types of illumination, another axis shows different types of geometry, and vertical axis shows estimated marginal means. What is clearly seen is that metal got largest gloss-related attributes for all 4 conditions. What is remarkable though, that such differences with respect to other materials like plastic and ceramics are strongest for directional light source I that contains high frequencies. This is visible on the following slides, which on the right shows exactly rendering under this strong illumination I that includes sunlight. Clearly we can see that gloss-related attributes are quite strong for this particular illumination, irrespectively of illumination. For the blob geometry that features low surface curvatures and overall smoothly changing surface, under smooth illumination A, E, and G, the differences in gloss-related appearance trend between metal and ceramic and plastic are strongly reduced. We use our massive rating data to train VGG network in order to predict attributes trends as measured by human subjects. So the loss is quite trivial in this case. We achieve high accuracy of our predictions. Our predictor is also stable with respect to small changes of the viewpoint, as it is shown in the first row. It increases gloss prediction with increasing geometric complexity, as it is shown in the second row, which is in agreement with work of Malone. Also, with reducing frequencies of illumination, perceived gloss is reduced, as it is shown in the third row, which is again in agreement with the literature. Let me discuss now some applications of our predictor. Our first application is located in 3D printing. And our goal is to find optimal varnish from a dictionary of varnishes that best matches perceived gloss for a target shape and illumination. In the first step, we print a test object, we apply different varnishes that change gloss, and this way we get a varnishes collection. We also measure BRDF for those different varnishes. Then we use measured BRDFs to render our target object that we are going to print under target illumination. We want to achieve desired gloss appearance as shown on the right image indicated by the red arrow. And then we use our predictor to analyze rendered images in order to select the best match between those two images. And then we apply this varnish to actually printed 3D object. Another application involves appearance editing using differentiable rendering. So we start from an image and we use our predictor to measure attributes trends. And now we would like to use differentiable rendering in order to find parameters of analytic reflectance models that fulfills these requirements concerning appearance attributes. So in some sense, we use differential rendering for BRDF fitting, and this animation shows the process as from some random parameters we converge to desired fit. What we can also do, we can impose requirements of different glossiness, and again through differential rendering we will find parameters of corresponding BRDFs. We can also match target glossiness for the object with the same geometry but under different illumination as shown in the middle, or different geometry under the same lighting as shown on the right. In this work, we study the effects of geometry and illumination on perceived appearance properties for different material categories. Our dataset, predictor, and code are available under following URL. Thank you for your attention.